So the next speaker is going to be Gal Chechik from NVIDIA. It's going to be a very interesting talk. So Gal, the stage is yours.
Hi. Okay, clicker. Yep. Thank you. Let's see that this works. Hi, everyone. Thanks for coming. I'm Gal Chechik. I am a professor at the Computer Science Department of Bar-Ilan, and I'm also leading the NVIDIA research group in Israel. This session is a lot about generative AI, and I'm also going to talk about generative AI, but I'm going to talk about the specific aspect of that. So I want to start with some context. Well, sorry. Yep, okay. I want to start with some context. If you go to any machine learning conference like 2-3 years ago, even AI Week, the standard workflow of machine learning would be you take, where's this show? Okay, the standard workflow would be you collect your label data, right? Then you train your model for that specific task with your label data, and then you deploy and infer on that data. And this recently changed, and the existing workflow is a lot about using what they call now foundation models. And in foundation models, you start with collecting a huge data set that is unlabeled. You train using self-supervised learning, which is basically you take your data and you generate like a side weird supervision task. For example, if you have a sentence, you can hide one word and predict it, or if you have an image, you can black out some patch and predict it. And once you finish this process, then you have a representation, and it turns out you can later take that representation, and that would be really useful for many downstream tasks. So the basic workflow has changed. As one example, and this clip paper has come up in several talks today. Amit talked about it, Idan talked about it. So you already know that this is a vision and language model that basically learn a joint embedding of words and images. So in a way that the word dog was going to be close to images of dogs. And you train it by a large set of image and text pairs. So this model, as you've already seen, is very useful. But the problem is, if you only train on these huge data sets that are not yours, then what about your own data? What about your own distribution? What about perhaps personal items or specific labels that you care about and were not in the huge data? So that's a problem I'm going to talk about today. So that, if we can try and combine somehow foundation models with learning for personal items, there are a lot of use cases. For example, imagine the time where we're going to have some smart agent, perhaps a robot in a home helping us make coffee. You want to interact with them in natural language, and perhaps you want to instruct them about specific items in your house. Hey, robot, make coffee in my favorite mug. The point is that once you have smart agents in your home, they need to be aware of the specific items that you have, right? And they cannot be pre-trained on the web for your specific items. Similarly, you want to solve problems of detection and segmentation for, let's here, locate my bag in a security video. Or if you have, we heard a question about image search. If you have a lake of your photos, you want to search your specific dress or jacket, not just any generic dress or jacket. So these were for discriminative tasks. We're also interested in generative tasks. You can create today wonderful images of dogs on the moon and dogs playing with cats. But what about my dog? This is Max. It's my dog. He's very beautiful, but it's not that smart. I wanted to read a book. Hey, Max, get a book from time to time. I would like to generate images of specific items, my pets, my family, Perhaps my child has a toy and you want to create a themed lunchbox based on his toy. So there are a lot of use cases for generative and discriminative with personalized items. How can we go about it? Previous approaches take the idea that you can take a model and fine-tune it for your data. So for example, you take a clip model and you show some images of Max, my dog, and then you can put an adapter on top of it. Or perhaps you can fine-tune the model itself. The danger with that is that you might ruin everything the model has already learned. So basically, the challenge is how can you teach the model about your personal items without hurting at all what it learned from the general distribution, which made it work so well. So our approach was inspired by work that we did on learning to name things or learning new words for concepts. And the idea was not to change the model, but actually learn to embed the visual content back into language. So the idea is this following. Think about a sentence like a photo of my dog, and this is going to be a photo of Max, right? And you know in language model, every concept is mapped to some vector. So our idea was that you're going to find how do you represent that vector such that once you encode it, it's going to be similar to the images of Max. So we're going to learn a new word in the language that corresponds to your specific item. Okay, and this is trained using like cycle consistency loss. There's also one smartness here. Sometimes just learning for personal items is not enough. You want to generalize, so you learn a general encoder that helps you find a good initial step for your optimization. Okay, we tested this on a large series of experiments. I'm just showing a few of these. In image retrieval problems, where you can give a complicated prompt, and in object detection, in instance segmentation, and this approach really worked much better than all other few-shot approaches. And the reason is because it could leverage the strength of these foundation models. Switching to generative models, so you've probably seen these images already. You can generate an image of a photo of a corgi dog riding a bike in Times Square, or you can control it using style. There's a lot of things you can do. But once again, I want to generate images of my personal items. Just a quick reminder how these diffusion models work. This is, again, self-supervised learning. You start with an image, you add noise to that, and then you use all these intermediate steps as a supervised learning problem. You train a deep network that receives a description and takes a noisy version and learn how to denoise it just a bit. And you train this for a long time. And now the question was, so how do we teach it to know our personal items? And the idea was similar to what we saw before. We're going to teach it a new word. So if you have that image, you can noise it, and then you control the new word here, S star, such that you learn a vector such that when it is fed to the transformer that controls the diffusion model, it would generate back roughly the same object that you want to train with. Okay, so here's a few examples of what it does. This is from an ICLR paper that was just accepted, even though this work has been out for a few months now and already got a lot of traction. A lot of people are playing with it. It's implemented on Hugging Face, so if you want to play with it, it's cool. Here are a few examples. Maybe you can see this statue, this headless statue. You teach it, oh, this is S star, and now you can control it with the full power of language. An oil painting of S star. This is my favorite. Elmo sitting in the same pose as S star. And a crochet of S star. So you can control the pose, you can control the style, everything that the language model already does. Here's another example. This striped cat. Again, painting of two S-star fishing on a boat, the themed lunchbox that you've already seen, etc. I want to highlight one aspect of this work that I found surprising. First of all, note that we only word a single vector, but still, this method can capture a lot of the complexity and the details of that specific object. Here's an example. Look at this teapot. This is what was generated using our model. And now, it's not the identical teapot, right? The handle is black, it's slightly different, the patches are not exact, but actually, it really captures the perceptual essence of this teapot, right? The patches are about the same, and if you can measure that, you can show that to raters, and they report that the variability, let's say, between the ground truth in our generation is about the same as the variability within the different images of that same object. By the way, just as a comparison, if you take other approaches and just try to describe that teapot with text using DALL-E or other approaches, of course you don't get the full richness of the visual objects because text is so much more semantic and vision gives you really different level of control. We quantify the quality of this, and I wanted to put up this slide because it's interesting how you measure the quality in this problem. There are actually two opposing metrics. One of them is how well does your generator generate that object that you've shown it? And the other one is how well can you control it with text, right? So if you take Max and you want to generate an image of Max, my dog, but if you tell it Max reading a book, then maybe it's not going to look exactly like Max because Max doesn't read books. And what I'm showing you here is these two axes, text quality, controllability, and image similarity. And we compare with a bunch of baselines. This is an automatic measure using clip space, and this is a human evaluation. There are a lot of other things you can do with this model. You can train several concepts, even though this is a bit hard. But we can combine style and a concept. For example, a photo of clock, S-clock, that's a new clock, in the style of the cat that you've seen before. So what's next? We extended this in two ways that this is submitted to a conference and I cannot show you the results yet, but two important ways. One is we accelerate the process about by 2 orders of magnitudes, and the idea is that you learn an encoder, again, that generalizes over a lot of different personalized items and give you a good initialization point for the optimization. And the other aspect is that we want to improve quality in those 2 metrics. We want better preserving the visual identity and also controllability. And here the insight was that perhaps just controlling everything with just a single word, a single vector in language, maybe that's not enough. And maybe we need a better editing, more richness, and there are other approaches that kind of fine-tune the full model. But here we took a very sophisticated editing. We really changed a small number of parameters in the model such that it learns the new concept but doesn't hurt everything else, and it also produces a very lightweight model. And of course, finally, so you've seen Max a lot. This is Max reading a book, Max cooking a gourmet meal, and 2 Max on a boat, a photo of Max wearing a hat. So I want to thank my collaborator. This is my team at NVIDIA Research, and our collaborators, Tel Aviv University, Dani, Amit, that gave an excellent talk earlier today, and you should watch, or talk with him or watch the recording or whatever. A lot of this work was led by Rinon Gal, Niv and Yoad, our PhD student that worked as intern in our group on several of the projects I showed here, and Yuval Atzmon, who is leading a lot of this work. Thank you so much.
Very interesting talk. Textual inversion is a method we all use nowadays, and it's very exciting that we have it developed in Israel. So, are there any questions from the audience to our speaker?
Yes.
One second.
I can repeat the
We'll
question.
use the, yes, but you'll be the next one.
What's the intuition of the speed up? The key intuition or...
Can you wait a second?
Yeah.
So the question was,
I can repeat the
Okay,
question. If I still remember, right? Okay, you mentioned the speed up of times 100, that this is one of the next steps, right? So, well, what's the key intuition of this speed up, and where do you think this speed up can go, let's say in 5-10 years? Can this go that far that we can do this real time?
anyone that is asked to predict 5 years ahead in generative AI, you need to be insane, right?
Generate.
Yes.
The ideas.
Yeah, generate. So here the main speedup was, there were several components. One main idea was to train an encoder that gives you a good initialization point. There are other tricks. Yes, I think if you look at the speedup that we had, let's say with nerf, that we can have instant nerf, we can have, especially with how hardware accelerates, we can get really, really fast with this. There are several challenges in creating something fast. It's easier to create something fast when you already know it, where it is close to something that have been trained. It's harder, it might take longer optimization, harder to generate things that are more rare. That you have less examples, etc.
Question. Hi. How many examples do you need for the training, and does it get better as you have more examples? And another question is, when you use human annotators, maybe Max looks the same to them, but to you it will look different. So.
Right. Excellent question. So first question was about the number of samples. All the examples I show you are like 3 to 5 samples. Our new work actually works pretty well, even with 1 sample. Of course, it depends. If you have something really unique, it's going to be hard. But it could work even with a single sample. The second question was about human evals. Right, when you ask personalized or specific questions, you often need experts. In a lot, you're right, and Max is one example where it's hard. In a lot of the experiments that we had very unique items, like the cat with the stripes, and there, or the teapot, and there it's easier to measure how similar it is visually.
A second. Can we pass the microphone?
I'll just repeat the question. Is this approach applicable for video? There are a lot of groups, I'm certain, that try to do now, generative AI text to video. I am certain that once we have fast enough and high quality enough text to video, we can also do personalization.
Yes, can you pass him the microphone?
Hi, you introduced a new concept and you perform another phase of training. But then you mentioned that you do not somehow destroy the previous knowledge that the model already acquired. How do you verify that, and how do you know that that doesn't happen compared to regular fine-tuning?
Right. So the reason that we don't hurt the original model is because we don't, in all the example I showed you, we don't fine-tune the model at all. We only change the input to the model. Therefore, there's no, we don't touch it, right? So every weight is preserved exactly as it was.
We have one more.
Hi. Is the process of text to image, is it reversible? Can you do both direction? And what you get if you run it, if possible, what you get if you run it in reverse mode? Meaning giving it a picture and asking it to describe the picture.
So I think you're talking about the problem of like image captioning, taking an image and describing it. Idan here did a lot of very interesting work about this. And this is an active field of research. Perhaps you're hinting about that it's going to be hard to do that with personalization, right? So how do you describe personal items? That's a really interesting question. We should do that. Idan, we should do that.
We look at it. Okay, so for more questions, please reach out to the speaker, and let's thank him.
Thank you all so much.